Computational chemistry showed how equations and computers can predict reactions, but beneath those calculations lies a deeper truth. Chemistry works only because the quantum world allows it to. Atoms bond, molecules form, and reactions proceed not by classical rules, but by probabilities, wave behavior, and quantized energy. Quantum chemistry is the field that explains chemistry at its most fundamental level, where physics and chemistry become inseparable. This is the learning studio, where chemistry is explained from first principles all the way down to the limits of what nature allows. And after seeing how computers model chemical behavior, the next logical step is to understand the quantum rules those models are built upon. Most people think quantum mechanics belongs only to physics, but in reality, chemistry cannot exist without it. For example, electrons do not orbit nuclei like planets around the sun. Instead, they exist as probability clouds, occupying specific energy states. The stability of atoms, the shape of molecules, and the strength of chemical bonds all arise from this quantum behavior. At the atomic level, quantum chemistry explains how electrons behave as both particles and waves. Their wave-like nature allows them to interfere, overlap, and form bonding and antibonding states when atoms come close together. Chemical bonds form not because electrons want to bond, but because certain quantum states lower the total energy of the system. This energy minimization, governed by quantum rules, is what makes molecules stable. The foundations of quantum chemistry were laid when Erwin Schrödinger introduced the wave equation that describes how electron probability distributions evolve. His work showed that electron behavior could be calculated mathematically rather than guessed. Soon after, Werner Heisenberg revealed that there are fundamental limits to how precisely position and momentum can be known, explaining why electrons cannot have exact trajectories like classical objects. As quantum ideas were applied to atoms and molecules, chemists began to understand atomic orbitals, electron spin, and molecular bonding in a new way. Linus Pauling used quantum principles to explain chemical bonding and molecular structure, showing how orbital overlap and electron pairing determine molecular shape and reactivity. Chemistry was no longer descriptive. It became mathematically grounded. Quantum chemistry also explains why the periodic table has its structure, why elements have characteristic properties, and why reactions follow specific pathways. The filling of electron orbitals, governed by quantum rules, determines valence, reactivity, and bonding patterns. Without quantum mechanics, the periodic trends we rely on would be inexplicable. As computing advanced, quantum chemistry became practical rather than purely theoretical. Approximations and numerical methods allowed chemists to apply quantum equations to real molecules, bridging the gap between abstract physics and usable chemical predictions. This made it possible to model reactions, materials, and biological molecules with increasing accuracy. Quantum chemistry also defines the limits of classical simulation. As molecules grow larger and electron interactions become more complex, calculations become exponentially harder. This challenge points toward the future, where quantum computers may simulate chemical systems that classical machines cannot, opening new possibilities for materials, energy, and drug discovery. And once we understand that chemistry itself is governed by quantum laws, the next question naturally follows. If quantum behavior defines chemistry, then how can machines learn from chemical data and discover new molecules beyond human intuition? That question takes us directly into the next episode, where we explore AI-driven chemical discovery and how algorithms are becoming partners in chemical innovation.